postdoc
Recording
in the
is
past 3
on.
years. It's how to enhance trustworthiness through NeuroSymbolic AI. And the use case that we have here is automated driving. It's a work that has been led by me, and I have collaborated with my colleagues, namely Arnaud Gottlieb, Najib Lazar, and Helge Spiker. The Arnaud Gottlieb and Helge Spiker are from SIMULA Research Laboratory, and Najib Lazar is a professor at University of Paris-Saclay, used to be my previous supervisor. So, Masood already gave me a very nice introduction, but briefly, my PhD has been in a conjoint between University of Oran one and University of Montpellier, and as I have said, as Masood said, I'm a research scientist at SIMULA, and my research and strength interests uh, span through these. So essentially, machine learning, qualitative reasoning, explainable AI, and recently automated driving. The project that I'll be presenting, although the context of the work that I'll be presenting is is financed by this project, AI for CCAM, where we aim to enhance trustworthiness in connected, cooperative, and automated driving. So it's a 3-year project. We have 14 partners, namely Skoda with us for um, uh, use cases, as well as other industrial partners. And Simula is the coordinator of this project. So I'll be giving some context first of all about what is neural AI, what is symbolic AI in the context of machine learning, and we'll try to build up from there into how we can apply these and conceive algorithms for automated driving using these concepts. So essentially, neural AI in machine learning is trying to model the data through a bunch of conjunctions of functions. So we got the name neural from neural networks because essentially they're algorithms that are used in order to learn, either to classify or to do something. So the basic notation for that is this. So you have some sort of input, you have some sort of output, and you want to simulate neural activity through functions. And the functions are generally nonlinear because it helps you capture patterns in data that usually are hard to capture. Essentially, what the brain does. And on the other hand, symbolic AI is a different way of representing knowledge. So we essentially rely on logical rules and human understandable representation. So it was formerly known as knowledge representation, and then in the context of machine learning, the community calls it concept learning. So can we learn a bunch of rules that model a data distribution or a certain phenomenon in the real world? And an example would be this. So imagine you would have some sort of data that would explain, that would give you or label whether a person would enjoy sports given certain criterias or certain symbols. And this data set has these features, and you would like to find what are the best features that would push the person that to enjoy sports. So this is called the hypothesis. So it's a conjunction of these symbolic features, and this is the concept that is learned. So what I have learned, what I would learn in symbolic AI or symbolic machine learning is essentially a conjunction of literals that would imply a certain decision. And this is very well studied in propositional logic and in everything that is a symbolic representation. Now, we have a little bit of good and bad for both sides between neural and symbolic AI. Some communities, they just like neural because they avoid doing the work. Essentially, they feed everything to the model, and they expected the model to be good. However, symbolic AI, you have a more handcrafted things that you need to put in. So you would need to analyze the data and then model the data manually in order to get something. So, um, which makes it highly interpretable and explainable, because we try to model everything with rules, and thus it's easy to understand when a decision is made and why a decision was made. So, one of the downsides is that even though we don't like it, but neural AI or neural networks or statistical machine learning has high accuracy. However, as I have said, it's really hard to explain. And on the other hand, symbolic AI can have, in most cases, low accuracy than neural AI, but you can easily explain why a decision was made. So there's this new community that came up in 2019 called NeuroSymbolic AI or NeuroSym community that essentially tries to take the best of both worlds. So they would say, okay, we know that models such as deep learning models are really strong, and we know that we can model semantically things using symbolic AI, which the deep neural net might not understand or might not model. So why don't we just combine the two, or use one in order to augment the other? So the goal is to essentially create a an AI system that is very powerful, in a sense where it can predict accurately, but it can also be interpreted, and it can be explained when a decision is made using the symbolic representation digested. So, a nice picture of it is this. So, if we consider, for instance, a data distribution of coronavirus images, you can try to model a coronavirus using a knowledge graph. So it could be the fact that it either has spikes or crowns, it has a capside, and this describes semantically what a coronavirus would look like, right? On the other hand, you can just take the image, feed it to a CNN, and then expect it to classify it as either being a coronavirus or not. And here, what we can do is essentially try to explain the neural network with this knowledge graph, or we can try to use this semantic representation in order to augment or enhance the interpretability or even the understanding of what the coronavirus is from the image. So, following in this line direction, we try to take this field of neurosymbolic AI and try to conceive our proper ways in order to apply them for automated driving. And again, this is still in the context of AI for CCAM. A little bit about automated driving. Uh, Automated driving is essentially pushing the car to drive by its own, and you would deploy a decision making system in the vehicle to um, perceive the environment and then make actions that a human would make in order to drive, essentially. And nowadays in Europe, the main problem is that we don't really trust these systems. That's why we don't have any automated driving vehicles yet, unlike the US. And that has a bunch of reasons that are, I think, that makes sense. So it's first of all due to the fact that we don't have trust in these AI decision systems, because the company doesn't really care. It gives you a black box, so you don't really know why was a decision made. There are legal and AI Act related constraints where we need to follow them in order to deploy any publicly available decision making system based on neural AI or decision or deep learning. And essentially, there are ethical issues such as, what if the car hits a pedestrian? Who's liable? Is it the company? Is it the person that buys the car? Or is it somebody else? Or is it the car itself or the algorithm? So essentially an AI system in the automated driving would look like this. So you would perceive a bunch of images through sensors. You would feed it to this box, which usually is a black box, and then it would give you a sequence of actions that would help you navigate and go uh, to parts of your journey. And one essential element is the perception part. So it is the part that helps you, that the model uses in order to understand where it is and what are the dynamics that are behind. And in order to do that, we usually rely on sensors that are both advanced and expensive, such as, I mean, the cameras are not that expensive, but we have radars, LiDARs, which are very expensive. So to give you a picture, a LiDAR costs around $30,000 in order to get 30, a 360-degree capture of the environment. And the LiDAR would give you a point clouds where essentially every object that is present, you see it as a bunch of points in a 3D space. And this helps the model understand what is going on. So one way of understanding that is just identifying the objects through the sensed images. So it can be identifying the categories of the objects, the dimension, the height, and so on. And uh, this is in the literature called quantitative scene understanding. So essentially identifying what are the objects, what are their dimensions, and what are their labels. And you might know it as object detection or object tracking and detection. And this, however, is quite problematic in a sense where you need to feed this to a model, and the model, all it sees is essentially just objects moving. It doesn't have any notion of spatial temporal dynamics. For instance, what is the meaning of a car overtaking? What is the meaning of a pedestrian trying to cross, and so on? So in your decision system, you would do this. Essentially, you take this, you would feed it to an attention-based model in this example, or a ResNet plus attention, and then it would give you a decision, which then you would use to control. Right. So it's exactly what I have explained before. Now we come to the problem of, okay, I have a decision. I have a model that has seen objects. It has given me a decision. I'm a passenger and the car stops. How do I explain to my passenger why the car stopped? And in order to do that, usually we just do this. So we try to show a heat map that says, the model probably concentrated on this part of the image or of the perception in order to stop. However, there is no semantical meaning to this, to these heat maps. First of all, because they do not embed spatial temporal interactions. They do not characterize what crossing the road means, what a stopping sign mean, and so on. So in AI for CCAM, what we try to do, I mean, the purpose of this work is to enhance this. So we would like to explain why a decision was made in a human understandable way, using dynamics. So using not just objects moving, but essentially expressing their movement, expressing their dynamics from the perception. And then we can use that to explain a scene, but also we can use it to enhance and go towards a more semantically aware automated driving. And you can imagine anything from embedding rules to embedding what crossing means in a set of symbols. So I'll start first of all by with the first more or less line of work, which is how to explain decisions. So, how can we explain decisions through the integration of symbolic knowledge to the neural decision making system? Just to recap, here's the chain of thought that we went through is if we see this perception, does it really hide any symbolic knowledge? So essentially, an example would be, can I represent this pedestrian moving here in blue? You'll see him in a second in a symbolic way that helps me understand his dynamic interaction. So, is he getting closer? Is he moving away? Is he moving towards me? Is he on my north side, on my west side, on my east side, and so on? And going from this ambition, we try to bring a field that was at the very beginning of artificial intelligence, before the whole hype about machine learning, which is qualitative reasoning. And qualitative reasoning is essentially a way to represent dynamics, spatial and temporal interactions between objects. So back in the day, before you would have a ChatGPT that gives you everything, you needed to model essentially a a car overtaking another car means qualitatively. So a bunch of algebras were created that reason in 2D space that help you give relations between objects. So essentially, an algebra is everything that has a language and that can be expressed over a set of variables. And luckily we have a lot of people that worked on this because I think in the mid 60s everyone was making algebras left and right, and they would express anything you would want using relations or qualitative relations, which in other words are essentially constraints. So how you would try to build such a representation of the scene that the decision making system is seeing or that the vehicle is seeing. You would take the perception, apply 3D detection and segmentation, essentially what I have showed you before, the objects that are moving. And then we have this algorithm that is called QXG Builder that helps you build spatiotemporal interactions using these algebras. And it would essentially be a graph, a knowledge graph representation, compact, and it embeds every spatial temporal interaction that is in the perceived scene, of course. Now, keep in mind that these two are very dependent. So if your object detection algorithm misses something, you can actually fix it using qualitative reasoning. So this is what makes the power, in a sense, of qualitative reasoning is essentially how to logically reason about possible positions through time, because you know that given the physics, it's impossible to jump from here to there. So this is how we build a qualitative representation. I will go in detail after. So QXG Builder, QXG is short for qualitative explainable graph, which is the representation that we have proposed for this context. So for the context of automated driving. And essentially what you would have is consider 4 frames, these objects where we can see the objects change position through time. I would want to build a graph where the edges are a sequence of evolving relations time by time. So it's one graph, but the edge is labeled with a sequence of spatial relations. And this would make the spatial temporal graph. More concretely, an algebra called Allen algebra is used in order to represent, for instance, positioning. I'll go to the example to make it simple. Assume we have these two objects at time t, This is what the boxes give me from the object detection, right? I can bring Allen algebra and try to build a relation that expresses the same thing. And how I would do that is essentially, if I consider this interval and this interval, I look up the relation in Allen's algebra, it would be overlapped by. If I consider this interval with this interval, then in Allen algebra, it would be precedes. And thus, I would have a symbolic or relational representation that expresses the positioning of one box with the other. And here I'm talking about boxes because object detection algorithms uh, return essentially just a box over the object. So it's an over approximation of the object in a form of a box. So it's as tight as possible, and this is how their models were trained. Now I can go further and I can represent the notion of distance, and I can just, since it's a BEV view of the environment, it's in an Euclidean space, I can compute the Euclidean distance, and then given a threshold, I would characterize what is very close, what is normal distance, and what is far, for instance. And now I'm able to take this visual aspect or this visual concept and just express it with this. If I go through time, if the object goes a little bit further, then it would be a different relation that expresses the position. And here, keep in mind that these relations are jointly exhaustive and pairwise disjoint. So essentially, they express every possible position you can have, and they cannot happen at the same time. So you can have a disjunction between these positions, but you cannot have a conjunction between them. You cannot say my object is before and after. So this is logically inconsistent. So the algebras were conceived in a way, in a property that we call GEPD, jointly exhaustive and pairwise disjoint. The algorithm, I try to keep it simple because there's this whole part that is very large, and I could not put it. So this is essentially was subject to a publication in the Journal of Artificial Intelligence, and another one in SAE, which is a journal for automated driving. But this is essentially the algorithm where for each pair of objects, you would try to compute the relation and then deduce other relations. So the algorithm was conceived in order to avoid making redundant computations of relations. But please feel free to look at the publications. And if you have any questions, you have my email. Now, the good thing about our algorithm is that it's parameterized by the qualitative algebra. So as I have said before, we have a bunch of qualitative algebras. So in the 60s, people, all they did was make an algebra. If they have a physical property, they would make an algebra that is GEPD, and they would publish it. So this is a parameter for us. And in the context of automated driving, we have found that representing the scene using qualitative distance algebra to express the distance, positioning algebra, which is essentially what I have explained before. Formally we call it rectangle algebra, and trajectory calculus. So, and this is essentially to express if an object is moving towards you, moving away, and so on and so forth. Bear with me because I have a demo at the end, so no spoilers. So people won't leave and let us alone. Now, we have also tried to exploit this representation that we have built. And in order to exploit it, we try to see what is catched by the use case provider. So we had a talk with Skoda, and we said, okay, what would be interesting for you? And they said explaining and identifying, for instance, relevant objects is very, very important. And we try to do that. So essentially, we try to take the qualitative representation, which is an equivalent representation of the perception. We take the perception, we feed it to a deep learning model, we get a decision, and then we try to take that decision and take the qualitative representation and then extract what could be the reason why a car took a certain action. So, uh, for example, I would say the car has stopped, and uh, I have 100 objects that have been detected, which are represented by the graph also. So, how can I know the exact cause that led to the car stopping? Is it because of the car that was parked 100 meters away? Or is it because of the pedestrian that is crossing? And here, the idea would be to identify the pedestrian. So, if I take my graph, I would prune everything, and then I would end up with just 5 objects, for instance, which are deemed to be the most interesting ones. And in order to do that, we try to take a data set where we had relevant, irrelevant objects in images. We built our qualitative graph, and we try to train a binary classifier where we labeled each object as being relevant or not relevant in the qualitative representation. And then we would essentially use that in order to prune any new scenes that emerge. So, for example, if the model learns that whenever there's a kid that is running towards the car, the ego vehicle, then the car stops and he is deemed relevant. This is an information that the model should capture. So, to show you this, um, I can give you a small way of doing it. So this is essentially what I have explained. So we take scenes, we build qualitative representations with them, and then we label objects as either being relevant or not, and then we train a model. Sorry, a binary classification model that would tell you what are the relevant objects that qualitatively make sense, that have a spatial temporal um, interaction that makes sense, for instance, for stopping. And keep in mind here, the action is an input also. So you have the interaction plus the decision taken by the deep learning model. And these are some characteristics about the data set. So new scenes is very well known for automated driving. So a lot of people use it to validate. And Drive LM is essentially a work on new scenes where people try to label objects, and they try to train large language models to take visual input and then identify relevant objects. And what we did as an experimental protocol is to see different algorithms, so simple and advanced algorithms, how they would perform on this qualitative representation in order to predict what is the relevance. So what you can see here is the recall is essentially the number of relevant objects that were identified from the total number, and the accuracy is what you have filtered out. And even though these results seem a little bit not that good, but you'll see compared to large language models, which are gas machines, how it performs. So here, this is the they have this competition on Drive LM on how large language models, a bunch of them, compare towards identifying the relevant objects. Keep in mind, in this context, we do not want to miss a lot of relevant objects, because if you miss a relevant object, it means that your decision making system is very bad. And what you can see here is that at that time, so this was the highest performer, where you had an accuracy of 76%, and the match is the recall essentially. So it's the number of relevant objects that were identified as relevant was 56. But then again, a guy came and took GPT-04, and he was able to achieve 93% recall in a sense. But the time when we compared, we saw that okay, we're we're essentially better. So it gives hope in a sense. Um, so this is the AUC, the result of the best fold, and I can show you essentially a demo on how this works. Just give me a second. Okay. Up. All right. I should start. So what you can see here is let me. This is essentially what this is Oslo, as might some of you might know, but
But
this is a real.
sorry, Nassim, I think still I'm looking at the demo slides.
You cannot see. Okay,
No,
hold
for
on.
me, at least from my side, no, I cannot see.
Let me see. Boom. Up. Window. Can you see this?
I
Let me
see.
launch again.
No, unfortunately, I see the demo slides now.
Uh, can you see like this? No. Yeah, I can see. I think there's a problem. I'm trying to give the. Okay, here. Let me just set this.
Okay, great.
Can you see?
Yes, yes.
Yeah. So it's a video, but unfortunately, I don't have it in playback. But here, what you see is essentially this is Oslo, where we try to test the whole uh, real time graph building, as well as filtering of the relevant objects. And as you can see here, there are multiple relevant objects, but the only ones that were highlighted by the model as being relevant are the people that are crossing. So here, if I take everything, it would be the people here crossing, it would be the car, it would be this person, it would be the bus, and so on. But what the model deemed interesting is essentially the fact. Let me just do this. Essentially, the fact that there is a pedestrian that went from a far distance to a normal distance to a close distance. And what you see here is essentially the positioning of doing this. And this symbolically represents a pedestrian crossing. So, one question that might come to mind is saying, okay, how can I read this? Because we have a mapping for this. So, essentially, we try to cluster all the relations that express crossing, that express this, that express that, and you can just easily label them and give them text in order to to continue or to facilitate communication. But this is essentially what you can use in order to explain why a decision was made. So the decision in this case was stopping, and the reason is this person. Um, Maybe if I can continue, I don't know if I have time, Masood. Uh, is
Yes,
there a
actually, I have like a kind of yeah. I don't know but if you need more time. Yeah, I think maybe
yeah,
yes.
so just to continue a little bit. So this was one part of the work. Another part was essentially try to, if you remember this schema, is try to take this knowledge and embed it here. And this is a preliminary work. I think we have good results, but essentially it's not yet thoroughly evaluated in order to be published. So here, what we try to do is first, the first slides I have showed you is how to explain this model using this, right? Now we want to go the other way around, how to augment this model using this representation. So here it's the qualitative graph or the qualitative explainable graph, and this is the model that you that is used in order to make the decision. So yeah, the animation was bad, but essentially what we do is we try to take the perception, the raw perception, augment it with the symbolic representation through a cross attention mechanism. So essentially, we take the embeddings of these, and we try to learn an alignment between the interaction of objects and the visual embeddings. And this, I can show you um, a small demo that would talk better, I think. Yeah, it's come in. It takes quite a while to load because I'm loading a model. But here essentially is to see whether semantic would help the model understand better to make a decision. So, can the model understand when the pedestrian is crossing? I should always either slow down or stop. Uh, can the model understand that when I'm driving fast, everybody needs to be away from me, or there's a dangerous situation behind me? So this is the intuition behind it, and waiting for the demo to start. What I would like more or less to highlight about this presentation is the fact that symbolic representation should not be something that we put aside in a sense, because a lot of efforts were made in order to think about how to model the world. And even though with all the AI that is coming, it's not something that should be disregarded, because it, even though it cannot be used to make decisions solely, it can be used to either enhance trustworthiness or even either to verify and test what these models give, for instance. And this is what we tried to tackle um, from the whole presentation. And it's about to start. The demo is on its way, I think.
Great.
The thing is, yeah, here. This is much better. I found the screen share tab.
Yes.
So here, essentially, I'll try to show you is this. So it's gonna take just a little bit of time, but of course, if we're our time is up, I can stop here.
But actually, I can, if you prefer, because already we have some questions. So take
Yeah,
the
yeah,
demo. I can, because already we have one question in the chat.
yeah,
So basically, Tore asks that while current automotive AI hardware is primarily visual centric, rely on CPU GPU architecture, could symbolic accelerators like the Teslin machine,
yeah,
or just an example, UIA, Teslin, Con Concotiem, or Flex IC ASICs offer a more efficient alternative for inference? Is the industry's reliance on the standard GPU NPU setup sufficient, or there is a strategic advantage to integrating symbolic logic hardware for edge case reasoning and power efficiency?
Hmm.
Yeah, very good question. Actually,
yeah.
it was also part of
That's
my
a good
question.
question.
Yeah.
Yeah, yeah. Yeah. So I'm aware that settling machines are very powerful to learn symbolic patterns. I mean, there's the whole community that backs it. However, the thing is, you're in a context where you cannot really just rely on uncertainty, because we're in a field where the minimal decision or wrong decision can lead to a fatality. So that's why they try to go accuracy first, but they want to explain gas machine in a sense. So from my understanding is that they essentially they cannot take any risks on performance, and they would rather uh, spend the effort on and spend the money on the accelerators in order to run these heavy models than to have this risk. And also one thing, I'm sorry, just one thing, it is that uh, the the OEMs, they do not want to have something that is related to networking for decision making, because they're afraid a lot about security, and essentially people trying to attack the decision making system.
Yes. If the demo is not started, I have also some questions. Maybe
Yeah, yeah,
it's a good time that
yeah.
I can ask. Actually, this is like the model that you chose. For example, like I mean the NeuroSymbolic AI, and also this basically Allen algorithm that you explained it. I mean, this like choosing the models, is it also related to the, for example, probably you have latency constraint to when you or proper time you also have the decision making that what to do. I mean that so then I feel accuracy and latency both are related to together. Do you have also some constraint there?
Yes. So that's a good question. There is a constraint about latency, so that's why we try to conceive an algorithm that runs while in real time, because you need something that runs in parallel with the decision making system. So to give you a little bit detail on the times, so 3D object detection on a BEV takes around 300 milliseconds. Okay.
Yes.
Um, the algorithm runs in about I think it's a half millisecond, or for 160 objects it runs for 200 milliseconds, 200 and something for 160 objects. I'm just giving you numbers about the the experimental validation.
Yeah, but
So
yes. Yeah.
but all of these and the decision making system would take around half a second to give you a decision.
Take a decision. Yeah,
You
but
see?
then is it in which hardware? I mean, like this is like
Yes. So so far, I mean, for concretely, Skoda has their own black box,
yeah.
so they have their own system. We don't really know what runs in it. That's why we had to conceive our decision making algorithm in order to make up for theirs, because the it's enclosed, so it's IP related. But um, I am suspecting it's TPUs,
Okay. Yeah.
because it's from Bosch, and I remember that there's a conference where in IV where they talked about how they are fans of TPUs in everything that is computing.
Yeah. Okay. Yeah. Nice. Thank you very much.
Thanks. Just maybe just one second to check on the on the demo,
Yeah. Sure. Yeah.
because my PC just froze out of nowhere. Ah, yes. Yeah. I think people got a little bit bored.
No, no, it was very interesting topic actually. So,
Yes, now should be it's running, and yeah. Essentially I loaded the different model, but I would like to give you just a small idea on how I mean how these semantics affect the decision making, and how they can the model more or less understands better when it sees some sort of a symbolic representation. It's like so it's essentially like text.
yeah,
So you're showing it visually, but you try to describe it also to caption it, and uh, aligning both the visual and the captioning gives you more or less. Yeah, I know. No, no, just 1 second. Up, fold two. So yeah, but again, this is something that I'm trying to get as good results with as possible.
yeah. This is
But yeah, again, it's so these. If you can see here,
yeah.
can you see this?
Yes, yes, yes.
This is essentially the accuracy of steering and of driving.
Mm,
So it's around 87 to 90 accuracy, which I mean, given the state of the art, is something. It's very comparable, and it runs reasonably fast. So yeah,
And Nassim, may I also ask,
yes,
regarding the direction, the latency numbers that you mentioned, that was the inference, right?
yes,
Okay.
that was for the
Yes.
inference. Yeah, a bit late on Friday.
Yeah.
Yes,
Yeah. Yeah.
Torres. I don't see you at the office, Torres.
Yeah, I think that yeah, he's on vacation, I guess.
Yeah, uh, perfect. Yeah, it's my computer is a bit
Yeah, this probably.
overloaded. Yeah,
Yeah, could be.
yeah, but it'll run. I'd like to go on my word.
Yeah, that would be interesting to see.
Perfect.
Oh,
Yeah.
great.
Yes. Here you go. So this is essentially it, right? So here, for instance, let me give you this example where it made a mistake, where it classified as being normal, where it is fast. Here, what I have noticed that the model is essentially between the borders of actions. So if it misses, it misses with a difference of fast to normal, essentially.
Mm,
And what you see here is the qualitative relations that it has attended to. So as I have showed you here, it's trying to do a cross attention between the image and the graph, and it is attending to some relations that are necessary. So here it's driving fast essentially because it knows that there are cars that are moving away from it, essentially. And here, what you can see, for instance, it says turning left, but uh, the second most highest, most rated action is um, is going straight. So if you take the softmax, you'd have a probability distribution. I tried to put the top two in order to have a safety mechanism, in a sense, something to fall back on. And the interesting part is that it is some sort. It's not saying going straight, going left sharply. But here, the more you go, the better the accuracy gets. Of course, the more samples you have, and this is an accuracy of top one essentially. But this is very experimental, so
So this is very,
still to find out how to make this much better.
very interesting. And may I
Yeah.
ask the numbers in the parentheses? They are the accuracy for like
You mean these?
yes, in the parentheses.
Now, this is the probability of taking an action.
Actions. Okay.
So, yeah, so the action of this is the ground truth. So the car actually is going straight and driving slow.
Okay.
And the model says, um, if I don't know the actions, then I would predict that I would go straight and slow.
Okay.
And
Yeah.
when you have a sequence of action, you have the planning essentially, which, for instance, goes from A to B. You would drive slow, turn left, drive fast, drive slow, and so on.
Very nice.
Yeah. So here, you see, here it's not bad. If it says not moving instead of slow, this is safe for me. It's a safer action for me to take. So yeah,
Right, that's
yeah. But yeah, so I had to stop because my PC is about to explode. But
nice.
yeah, um, uh, that's it for me.
Okay,
Thank you
great.
for your
So
talk.
thank you very much, Nassim. And we have some more questions, I guess.
Yeah, yeah.
Let me see from Tora. Mm, Toward the tri-hybrid automotive architecture, where standard CPU GPU stacks are augmented by Teslin machines ASIC to handle symbolic reasoning specifically. Do you see this extreme heterogeneity as the necessary step to bridge the gap between raw perceptions and logical decision making in autonomous vehicles?
I would need to read more about the i6 tour to answer this.
Okay.
It's a bit because I assume it's a way to digest images, right? Settling machines, i6. Um, I'm aware of settling machines, short, but uh, maybe if they have a way to digest images as well as symbolic representation, I think yes,
This is
it would bridge the gap. Yeah,
great.
yeah,
Yeah, that was very nice, Nassim. So because we talk about basically today was NeuroSymbolic AI that it was new, and also how we can detect the objects, also moving by frame.
yeah.
And then basically we have latency constraint, also improving the accuracy. Also we discussed about the hardware, also your system. We have the demo. So that was very nice.
Thank you,
Thank you very much.
thank you.
Actually, at the end, so I just stop recording here now. If there is, but before recording, if there are more questions, so please let me know if there are any more questions here. Okay, so if not, I can stop recording here.